supersymmetries, because I sort of lose control over the theory. Supersymmetry gives you these powerful non-renormalization theorems, BPS conditions, and things like that. So usually it's a good idea to keep some supersymmetries, at least if you want to be able to do calculations and trust your answers. So from a sort of Kaluza-Klein supergravity point of view, one of the questions that we'd like to ask or try to answer is what manifolds should we choose over here so we can preserve some supersymmetries while breaking some others. So if we talk about the MSSM or the sort of minimally supersymmetric standard model, the thing that people like to talk about for superpartners at the LHC, we usually like the four-dimensional n=1 theory, four real supercharges. So is it possible to start with one of these higher dimensional theories, like hadrotic string, or type 2 string, or 11-dimensional supergravity, and reduce down to 4 dimensions to give you an n=1 theory? And one way to do that is the so-called Calabi-Yau compactifications. But more generally, the question that I could look at a little bit is how do you choose X to preserve some, but maybe not all, supersymmetries? And the basic snapshot is the internal manifold has some geometry, has some shape or something like that. The geometry obviously determines the symmetries of the manifold, but I'll also make the claim that the geometry also determines the amount of supersymmetry that's preserved in the Kaluza-Klein reduction. So to do that, I have to consider how do I look for supersymmetries, which is sort of how do I look for supercharges or preserved supercharges. What I mean by a supersymmetric sort of compactification is I can have a theory with a supersymmetric vacuum. So I have a vacuum state over here, and supersymmetric vacuum is something that's annihilated by all the supercharges, or at least by some fraction of the supercharges. Well, if I have a supersymmetric vacuum, Q vacuum equals 0, then I can sandwich a commutator like that, and it should be equal to 0. Q either acts on the left or acts on the right to give me 0. Now, I'm assuming phi is just some other field in my theory. The Q commutator of phi is what generates supersymmetric transformations on phi. So if I had a supersymmetric vacuum, I'm basically looking for a configuration of fields such that the supersymmetry variation of the fields equals to 0. I want that to hold for all fields in my theory. So I want to find a background such that supersymmetry variations on the background is equal to 0. I can further break up the background fields into fermions and bosons, because that's what supersymmetry does for you. So what I want to do is I want the variation of fermion fields to be equal to 0, and the variation of boson fields to be equal to 0 as well. But the variation of fermion is a boson, variation of boson is a fermion. If I look for backgrounds without fermions, so I don't turn on any background fermions, I have a purely bosonic background, then the fermion is equal to 0 over here, which means the delta boson equals 0 is automatically satisfied, just because I don't have any fermions in the background. What is not automatically satisfied is the delta fermion equation over here. So I need to find delta fermion equals 0. So I want to solve the equation delta fermions equals to 0 for all fermions in my theory. That's how I find a supersymmetric background. So we consider, if I had a supergravity theory, at a very minimum, I would have a metric field, or a Vielbein over here, and I have a gravitino psi mu. I might have other stuff as well, but this is a very basic minimum. It's not supergravity if it doesn't have a metric and a gravitino. So as I said, if the background is purely bosonic, then the gravitino field itself is equal to 0. So the variation of the Vielbein equals 0 is automatic. The gravitino might be equal to 0, but the variation of the gravitino is not guaranteed equal to 0 unless d mu epsilon is equal to 0. So a condition for unbroken supersymmetry is that d mu epsilon equals to 0. And this is known as a Killing-Spinner equation. I, on purpose, didn't exactly tell you what this curly d is. It's some generalized covariant derivative, which may or may not be the ordinary covariant derivative. And it's just a word of caution. In extended supergravity theories, sometimes there's more than one fermion field needed to set. There might be dilatonos, gauginos, all of those have to be set equal to 0 to find a supersymmetric background. But I'm just going to focus on the simple case. Let's say we only had a gravitino, and we want to solve that equation here. This is known as the Killing spinor equation. Solutions to this equation are called Killing spinors. And so if you remember the idea of a Killing vector, the isometries of my internal manifold are related to Killing vectors, and now I'm just going to say the supersymmetries of my internal manifold are related to the existence of Killing spinors. So let's look at the Killing spinor equation. So again, this is my standard Kaluza-Klein type reduction. I have a capital D dimensional manifold with x capital M coordinates over here. And I split it into a lower dimensional manifold, made a little d, and an internal manifold of n dimensions like that, with space-time coordinates and internal space coordinates. Now my higher dimensional fields can be split up into background fields plus fluctuation fields. And people often talk about so-called flux compactifications, various interesting backgrounds. I'm just going to look at the simple case, at least for today, where the background is basically just internal metric. The only thing I do is I have a manifold which might not be a torus. It might be a curved internal manifold. Because it's a curved internal manifold, I have a non-trivial internal metric Gij. Other than non-trivial Gij, nothing else is turned on in the background. In that case, the Killing spinor equation is basically just ordinary covariant derivative on my internal space is equal to 0. This Killing spinor equation is also sometimes known as parallel spinors. It's parallel in the sense that it's covariantly constant. So if you think about parallel transporters, so the spinors more or less just don't rotate around, is the notion of this equation here, covariantly constant spinor. So without any additional crazy fields turned on in my internal manifold, pure geometry, the existence of Killing spinors is just related to how many covariantly constant spinors I can find on my internal space. Now a spinor has a spinor index. So this might be a 16 component spinor, 32 component spinor, something like that. So if I actually wrote this out in terms of components, I could have a various number of solutions, and so I can have partially broken supersymmetry where this is equal, where I can solve this equation for maybe 8 out of 16 components of the spinor or something like that. So I can have maximal supersymmetry, partially broken supersymmetry, things like that. And how much supersymmetry I have depends on counting how many parallel spinors, or how many Killing spinors I have on XS. So what we like to do is to be able to look for Killing spinors, count how many Killing spinors we can find in an internal manifold. Now there's various ways of doing that. The most straightforward way that they think of is on a Killing spinor equation. Nabla I epsilon equals 0. We have epsilon equals 0. It's a differential equation. It's a coupled linear differential equations. Solve that. So just solve the equations. Well, it turns out that's not always such a fun thing to do. So another trick is to look for integrability. If I take the Killing spinor equation, hit it with another covariant derivative, and put in a commutator over here, this should still be equal to 0. A commutator of two covariant derivatives is a very nice geometric object in GR. That's measuring curvature. So I can solve this integrability equation. The nice thing about this is it's no longer a differential equation on epsilon. That's very helpful. In fact, from a geometric point of view, this is measuring parallel transport. And so this is a way locally measuring what happens to your spinor epsilon as you sort of move around your internal manifold. If I move around in a closed loop, I form what's called the holonomy group. And so it's very closely related to Agrability, is studying the so-called holonomy of the internal manifold. So let's look at the integrability condition. Exactly as I said, you would have a commutator of two covariant derivatives. It gives you curvature. This is curvature acting on a spinor. So it's a Riemann tensor contracted with this antisymmetric 2-index gamma over here. There's various tricks I can do with this equation. One thing I can do is I can contract this with additional gamma, multiply this equation on the left by gamma j over here. Now, three gamma matrices like that. What I can do is I can manipulate this. Gamma KLs by definition, or by conventional definition here, the antisymmetric product of the gamma matrices here. Gamma j multiplied on the left is not automatically antisymmetric. So if I use the right gamma matrix identities, I can form that into a 3-index antisymmetric gamma plus some sort of commutator terms, or some contraction, some Clifford algebra terms over here that give you a 1 gamma term. Well, this is the ordinary curvature. This is the ordinary Riemannian curvature. Nothing special about my internal manifold. So if I antisymmetrize on 3 indices over here, it's one of the Bianchi type identities, that gives you 0. And it gives you this 1 gamma term left over with this metric contraction, which changes Riemann into Ricci. So integrability tells you something interesting, at least I hope it does, which is you have RIL gamma L epsilon. If I have a Ricci flat manifold, think vacuum Einstein equation. Vacuum Einstein equation is RIL equals 0. If I have a Ricci flat internal manifold, then this integrability is automatically solved. So this is sort of compatible with the vacuum Einstein. The fun thing is in an Euclidean manifold, I can actually, so if I compactify space only, which is the standard compactification, on a Euclidean internal manifold, I can actually do the converse as well. I can go in the opposite direction. The existence of a Euclidean spinor gives me integrability over here. If I have integrability, I have this Ricci condition like that. If I take this Ricci condition over here, which is this part over here, I just multiply on the left. If something's equal to 0, I can left multiply and still get 0. But I didn't choose this to be a random sort of factor. This factor is basically the same as that factor over here. Then I have 2 gamma matrices, which I could combine into the antisymmetric product plus a metric component. Like that. I put an I hat over here to fix I hat. I hat is like number 5 or something like that, or number 7. I'm not summing over I hat, which is why I specifically singled out I hat over here. When I do that, this thing is symmetric in J and K, so antisymmetric gamma is gone. This metric gives me a contraction of the JK indices. Now on the Euclidean manifold, this is basically, the metric is basically positive definite over here. So this is a positive definite contraction. This gives me sort of, in a way, the norm of R I hat J, like that. And it's equal to 0. So I have a positive sum of squares equals to 0, which means each independent term in R I hat J must be equal to 0. And I hat could have been the number 7, could have been the number 8, could have been the number 9. You can convince yourself that, in fact, all components of internal Ricci have to be equal to 0, which means this integrability condition implies Ricci flatness of my internal manifold. So Ricci flatness is a necessary but not necessarily sufficient condition for preserving supersymmetry. Now this depended on having a positive definite metric, so that the Lorentzian signature, or things where I use a different connection, can be a little bit more complicated. So one thing we've learned is to preserve supersymmetry with this pure geometry is I need a Ricci flat internal manifold. If I can think a little bit more about that, so let me go back to my integrability equation over here. As I said, the commutator to covariant derivatives basically is telling you something about parallel transport. And by parallel transport, a spinor along a closed loop, either a spinor parallel transports back into itself, or it parallel transports into a rotated version of itself. And the group of actions under these parallel transports in a circle is known as the holonomy group. And for a n-dimensional manifold, the general structure group is SON in the tangent space. And so the holonomy, how much it can rotate, should be a subgroup of SON. Now, I want to solve the Killing-Spinner equation, which means I want the integrability to be 0. I want this parallel transport on a spinner to give you 0. I want the spinner to basically rotate back into itself. So the number of preserved supersymmetries is related to the number of singlets in the decomposition of the spinner in the holonomy group. The holonomy has been classified by Berger, and a very generic metric, as I said, has this SON holonomy group. Basically, spinners or vectors, things parallel transport, can rotate into any sort of way you want. However, with so-called special holonomies, which are restricted parts inside SON, you can have different sort of situations. As I said, if you want supersymmetry, you want Ricci flatness. And so only some of these holonomies are compatible with Ricci flatness. And probably the most famous example might be the so-called SUN things over here. For SU3, which is a 6 real dimensional manifold, SU3 fits inside SO6 after all. And you end up with what's called a Calabi-Yau. And for Ricci flattened Kähler, SU3 holonomy is the Calabi-Yau case. You can do the same type of classification for Lorentzian signature manifolds. I won't talk about that, but that's a little bit more complicated story. So I'm going to wrap up today just by saying a few words of Calabi-Yau for fun. But before I do that, let me just step through a few other cases. So let me revisit the idea of torus compactifications. If I had trivial holonomy, a torus is flat. If I parallel transport things, they don't rotate. That's what it means to have a flat space. If I had a flat space over here, the covariant derivative on epsilon is just a partial derivative on epsilon. If the partial derivative of epsilon equals 0, then epsilon is a constant spinner. And for as many components of epsilon there are that many linearly independent constant spinners. I haven't broken any supersymmetry. If epsilon is an 8-component spinner, then I can choose epsilon 1 constant, epsilon 2 constant, epsilon 3 constant, all the way down to epsilon 8 equals constant. 8 linearly independent killing spinners, 8 supersymmetries out of 8 supersymmetries, or whatever numbers. Okay. So flat space doesn't break any supersymmetries. And that means that I looked at the table I gave you yesterday, and looked at a subset of that. I can do torus reductions of the 32 supercharged theory, which is the 11-dimensional theory over here. And I can just go straight down the column of the table over here to give you a 32 supercharged theories like that. I can also start with 16 supercharges. This is a heteronics theory in 10 dimensions, and they can all reduce down on a torus like that. I can also have the 8 supercharged theory, the 1, 0 theory in 6 dimensions, and reduce that in a torus. What's a little bit more interesting is special holonomy. Let me give you an example of SE2 holonomy. So SE2 holonomy is supposed to fit inside SO4, a 4 real dimensional manifold. And the fun thing about SO4 is you can decompose that into 2 SU2s. The spinner of SO4, this is very much like the standard decomposition of SO1, 3. Except this is actually SU2s instead of SL2s. 4 decomposes, the spinner decomposes as 2, 1 plus 1, 2. And SU2 plus and minus is basically the chirality as measured by gamma phi. What that means, and this is special to 4 dimensions, is the integrability condition over here can be rewritten in terms of self-dual and anti-self-dual components of Riemann. What I mean by self-dual and anti-self-dual is Riemann has index pairs. The first 2 index ij, the second 2 indices alpha, beta, A, B. 2 antisymmetric indices A, B can be dualized using the epsilon tensor in 4 dimensions. So I can form self-dual and anti-self-dual Riemanns, R plus or minuses, like that. when the AB indices are self-dual and anti-self-dual, working with this gamma matrix over here, you can show that they project out onto anti-self-dual and self-dual, well, positive and negative chirality epsilons like that. So one equation here is equivalent to both conditions, this and that equals to 0. So it's a clever way to solve these equations. If I chose a self-dual connection, in the sense, if I found a manifold such that Riemann minus is equal to 0, then this equation is automatically solved. I only need to solve this equation. I can solve this equation in the most simplistic manner by setting epsilon minus equal to 0. So if I choose a self-dual connection, R minus equals to 0, and I choose epsilon minus equal to 0, I have solved my integrability. However, by making a choice, I said nothing about epsilon plus. So here's the idea. I choose R minus equals to 0, and I choose epsilon minus equal to 0, so that this equation is also true. Since I have said nothing about epsilon plus, all possible epsilon pluses are allowed. I should have also mentioned that when I look at integrability, integrability is basically the obstruction to finding Killing spinors. The Killing spinor equation is these first order differential equations. Those differential equations, at least locally, always have a solution unless obstructed by integrability. So solving the integrability equation is basically the same as finding Killing spinors, or counting Killing spinors. I still have to actually solve the equation to get the Killing spinor, but counting Killing spinors is easy like that. So what I've done over here, by choosing a self-dual connection, or choosing R minus equal to 0, is basically I've taken my SO4 holonomy and I've broke it down into SE2 only. And so I just focus on the SE2 minus over here. I have a doublet over here. And this is a singlet of SE2 minus. So this is a doublet of SE2 plus. If I ignore SE2 plus, this is really two singlets. So the decomposition is the four-dimensional spinor is 2 plus 1 plus 1 under SE2 minus. So in terms of counting singlets of the holonomy group, singlets of SE2, I have 2 singlets out of 4 possible states. That means I've preserved half of the supersymmetries. I've preserved the supersymmetries with epsilon plus, basically. That's sometimes referred to as a half BPS or half supersymmetric sort of compactification. So compact manifolds with SE2 holonomy, well, up to moduli, there's basically just one, which is known as the K3 surface. And so the SE2 holonomy for the compact case is basically the story of the so-called K3 surfaces. And they're used quite often in various situations. Paul Aspinwall has a very nice sort of review on K3 surfaces if you wanted to think a little bit more about that. What I really like to do is say a little bit more about SE3 holonomy, which is the Calabi-Yau case. And so here I have a 6th real dimensional manifold with the tangent space SO6, which is basically equivalent to SU4. So what I want to do is to take the 4-dimensional spinor of SO6 and decompose that into SE3 holonomy over here. So 4 goes to 3 plus 1, basically. There's one singlet out of 4 components over here. So a Calabi-Yau compactification preserves 1/4 of the original supersymmetries. So this is Ricci, Flat, and Kaler as precisely SE3 holonomy preserves 1/4 of the supersymmetries. And so Calabi-Yau compactifications were prominent in string theory from a phenomenological point of view. This is the original idea of heterotic theory in Calabi-Yau. It is a 16 supercharged theory in 10 dimensions, preserving 1/4, gives you 4 preserved supersymmetries in 4 dimensions. That gives me 4-dimensional n equals 1 theory. So we wanted to do traditional string phenomenology on the Calabi-Yau manifold. This is what he did, heterotic and Calabi-Yau. However, it's also interesting that you can put type 2 theory or 11-dimensional supergravity on Calabi-Yau. Both 11-dimensional supergravity and the type 2 strings start with 32 supercharges. You preserve 1/4 of 32 2, you get 8 supercharged theory, which means in 4 dimensions you get n equals 2 theory. In 5 dimensions, in this crazy notation, you also get 5-dimensional n equals 2. These are 8 supercharged theories over here. So what we've learned in this case, at least, if I wanted to preserve one part of the supersymmetries with a 6-dimensional compact manifold, I choose it to be Calabi-Yau. But let me actually go back to the Kluser-Klein idea a little bit. And I'm afraid I'll just be a little bit sketchy on this, but it's sort of not too different. In principle, it's not too different than what I said before in terms of expanding on Fourier modes, except instead of expanding on Fourier modes on a circle, you expand on harmonics on the Calabi-Yau manifold. So I do the same Kluser-Klein sort of idea. I take my 10-dimensional field to my higher dimensional field, I split them off into background plus fluctuations. The fluctuations can be decomposed into harmonics, f of y's over here, where the harmonics are not just e to the I n y over r, they are more complicated type of harmonics. But it's the same idea. Once I decompose like that, I can look for the lower dimensional equations of phi of x u basically. So in supergravity theory, I have bosonic fields and fermions. I won't talk about fermions, but I'll focus just a little bit on the bosons. And the standard bosonic fields we'll have to deal with are scalars, p-forms, and the metric. So scalar field is just like what I started today with, the idea of compactifying a scalar field. So if I had a higher dimensional scalar, I had a Laplacian or a Laplacian operator, let me just call it delta 0, that's minus box. It just has the familiar decomposition in terms of lower dimensional box and internal box like that. And so what happens is I decompose in terms of harmonics. So I solve the Laplacian equation on my internal manifold with an eigenvalue lambda. When I do that, my lower dimensional Laplacian, my higher dimensional Laplacian is lower dimensional Laplacian plus my eigenvalue of my scalar equation over here. So the lambda over here, the eigenvalue of my internal Laplacian over here serves as a mass of my lower dimensional theory. That's how my Kluser-Klein tower originates. So by knowing the spectrum of the Laplacian on my internal manifold, I have determined the spectrum in terms of masses of my lower dimensional scalars. There's a special case, of course, which is the zero mode. For compact internal manifolds, I can always choose f equals constant. There's a trivial way to solve Laplace's equation. F equals constant, lambda equals 0. That gives me a massless particle without lambda over here. It gives me a massless particle in 4 dimensions. You can do a similar analysis for p-form gauge fields. Here it's a little bit more complicated. But a natural thing to realize is if I have f equals dA, the standard equation of motion is d star f equals 0. There's a Bianchi identity, df equals 0, equation of motion d star f equals 0. If I choose Lorentz gauge, d star a equals 0, then it turns out that the equation of motion d star f equals 0 has a nice geometric way of writing it in terms of what's called the Hodge-Duran operator, which is basically the Laplacian p-forms in Lorentz gauge. This is basically box. This is basically box. This is box A mu equals 0. So I guess I don't have time to go through all the details, but let me just highlight that this is box A mu equals 0, except it's sort of box with curved space. There might be some different sort of curvature issues as well. So if I do a Kluser-Klein decomposition, I take my p-form in higher dimensions and break it up into lower dimensional q-forms and internal p minus q-forms like that. The Laplacian breaks up into space-time Laplacian plus internal Laplacian. I do the exact same trick. I look for eigenstates over here of my internal Laplacian. And if I want to count zero modes, so the eigenstates, or the spectrum of the Laplacian gives me the Kluser-Klein spectrum. Zero modes, on the other hand,